A diffraction grating works very similarly to a two-slit interference pattern. The difference being is that you have a many lines etched into a photographic film or a piece of glass. And these many lines cause an interference pattern that produces maxima. Rather than having faint edges, it has very sharp edges. What you need to know is that the sine of the angle for these maxima is equal to the order number times the wavelength over d. This d is also the slit spacing. Instead of being given the slit spacing and for a diffraction grating, you're often told how many lines there are per distance, often in centimeters. So you might be told that there are 10,000 lines per centimeter. Now, to figure out what the slit spacing is, if you think about what the slit spacing it is, it's how many centimeters there are per line. So really, you just have to take the reciprocal of this number, and you'll get what you need, which is 1 over 10,000 centimeters per line. And at that point, you actually would maybe have to convert that. Well, you would definitely have to convert that to meters. So it's not a challenge, but the one thing that does make this different than a two-slit experiment is that you're going to have to come up with d with other given information, whereas in a two-slit interference problem, you'll actually just be given the slit spacing. Now let's do an example. Determine the angular position of the first and second order maxima for light of wavelength 400 nanometers and 700 nanometers incident on a grating containing 10,000 lines per centimeter. Okay, so we have a wavelength of 400 nanometers, which is 4 times 10 to the negative 7 meters, and also one that is 700 nanometers, which is 10 times 10 to the negative 7 meters. And we're looking for the first and second order, so we're going to have m equals 1 and m equals 2. So for the first one, we'll do sine of the angle. I'm going to call it angle 400 so we know which one we're working with, equals m, and we're going to use 1 for the first one, times the wavelength, 4 times 10 to the negative 7 meters over d. Now this is what I said, is we have to find d, and if we have 10,000 lines per centimeter, then d is going to be the reciprocal of that. And I get 1 times 10 to the negative 4 centimeters. But I need that in meters, and so I'm going to have to divide it by 100 again, and I get that that is equal to 1 times 10 to the negative 6 meters. So that's going to be our d. Okay, so if I put that in here, 1 times 10 to the negative 6 meters, we're going to have to take the inverse sine to get that angle. And that angle for us is going to be 23.6 degrees. For 700, the only thing that's going to change is wavelength. Slit spacing is still the same. And if we do the inverse sine of the number we get, we're going to have an angle of 44.4 degrees. Okay, so that's for the first order. Now the second order, the only thing that's going to change is that we're now going to have a 2 for our order number. That'll give us an angle for the 400 of 53 degrees. Now when I do this for 700, something interesting is going to happen. I have 2 times 7 times 10 to the negative 7 meters over 1 times 10 to the negative 6 meters. This number here is greater than 1. If you try to plug it in your calculator and take the inverse sine, it's going to say error. You can't do that. And what that means is there is no second order maximum. Does not exist for the second order maximum. So you can only diffract using these gratings so far. These are pretty simple problems. This is about all you do with these.